Good morning. My name is Drew Farnsworth, and I'm going to be giving a presentation about high-performance computing in colocation. For that, I just want to thank AFCOM for coordinating this event. They always do a good job of connecting end users with, people who aren't necessarily vendors, which is a great service to everybody who needs it. So let's get started. If I have a little bit of a speech impediment, it's because my 1-year-old daughter was very excited about her bath yesterday, and she head-butted me in the lip, so I have a little bit of a bruise there. But let's get started.
More to come.
Okay, so lightning in a rack. Just want to talk, high-performance computing is here. It is something that is happening right now, and is happening in all sectors of computation. HPC is important. There's so many applications that are coming out that are using this architecture, and it really is only going to grow. And colocation, especially custom colocation, is a very good fit for this kind of HPC. So we'll get into that. So what is HPC, first of all? Well, it's basically computation that goes over very large computation sets, and it's sort of started with this progenitor of supercomputing, the Cray supercomputers. So it's taking very, very complex computation, usually parallelizing it so that not just one little section is done at a time, but many different processors are actually doing simultaneous computation. So basically, one of the definitions for HPC is something that runs at teraflops or above. So you think a lot of your computers that you use maybe are gigaflops. So flops is floating point operations per second. We're talking computers now that run petaflops. So you go, giga, tera, peta, and we're looking now to actually get faster, and it's grown at an almost exponential rate. And then, the kind of common parlance for this is supercomputer. So that's what we're talking about today. We're basically talking about supercomputers and how that is moving into the mainstream. Now, one of the problems with that is they create a huge, huge, huge amount of heat. This Cray computer, all the way back in 1960, produced about 115 kW of heat just in this tiny frame, about 200 square feet. And generally, they have specialized designs. So we're not talking regular servers or infrastructure they usually use. They use things like application-specific instruction circuits. So very, very complex types of computation. So one big example, this is the Sunway Taihu Lite. It's currently the fastest supercomputer on the top 500 list. And just to go through it really quick, as an example of how fast this is and how complex it is, this one computer, which all works together, is 15 megawatts of power. It has 10 million compute cores and runs at 93 petaflops, which is about 3 times faster than the previous record. It uses closed-coupled liquid water cooling, and they have what they call a hybrid network, but really it's InfiniBand, and it's incredibly dense, so about 1,200 watts per square foot. So this is kind of the highest end that we could possibly talk about with this HPC. But before we do that, let's kind of take it to the new generation, which is actually small HPC. So very small parallelized computation. In this case, we're talking about just a regular card that would go in a regular PC called a GPU. So that's a graphics processing unit. They're becoming commoditized because these are things that are just found in regular computers. For example, the NVIDIA Tesla GPU can run massively parallel computation at basically server prices. So, something like this, actually one of these costs about $3,000. You can get a 4U server that has 8 of these GPUs in it for 34 teraflops, which is faster than anything that was available in the early 90s, for instance. And it fits in 4U in a rack. And the prices are coming down so that it's not just the big guys like the US government or the the Chinese government or something like a large actor, or Exxon, like something like that, it's actually commoditized to the point where very, very small startups can actually use the same technology. So that was all very technical, but I just wanted to get it out of the way because it matters. There's a huge growth in HPC. It was actually outpacing the rest of the market last year in 2015. It had 11% growth, which blew away all the analyst projections. And that's because there are these huge performance benefits, orders of magnitude faster than conventional architectures. So, as an example, you have graphical rendering. If you have two different renderings at the same resolution and quality level, the high-end graphics processors actually do it about 6 or 7 times faster than the regular Intel architecture. So that's because that they're using a parallel architecture. So it is, kind of imagine a serial processor, which is I guess that was Siri talking, which we'll talk about in a second. A serial processor you kind of imagine as a machine gun. It uses the same barrel and just shoots a lot of bullets out of that same barrel. Whereas you can imagine a parallel processor being a whole line of a firing line where each person has their own gun. So let's say this machine gun can shoot 500 rounds a minute. Let's say this can actually shoot, you put 1,000 people together, 1,000 rounds a second. So you could also upgrade each one of those. Instead of muskets, you can have M16s. And then that's the way that this is scaling. So that instead of being able to, using a machine gun to get faster and faster and faster in the same barrel, you have many, many barrels that might not be as fast as that, but you put them all together and it ends up being faster. And the reason I want to bring that up is that that's everywhere now. Every single computer that you use has multi-cores. And that is only going to grow. So in your everyday life, you are already using something that is akin to this high-performance computing. And we're actually reaching the theoretical limit of serial computing right now. It breaks down. We can't get any faster than that. So there's no choice at all but to go parallel. And so we're already living in that HPC world. And why that's important is that those power densities and that heating that comes out of that is so much higher than anything that we're used to seeing in data centers. So data centers are going to have to adapt to that to make sure that they can cool this kind of parallel computation. All right, so what is HPC for? Well, originally it was for cryptography, government. That's how computing got started. Alan Turing made a computer to break the Enigma code of the Germans in World War II. It moved on to things like physical modeling, like oil and gas or computational fluid dynamics. NASA used CFD for a long time to create, to be able to make the space shuttle work. It's used weather forecasting these days. You look at all the projections that were happening with Matthew, all that came from high-performance computers. There are the European model or the American model. Those each come from some kind of HPC array somewhere in the world. Climate research, go through. Molecular modeling, so instead of having to run chemical tests to see if a certain drug is working for pharmaceuticals, they're actually using molecular modeling, and they're able to save so much cost by running it through a computation set as opposed to actually doing the chemistry. And then big data. This is really where we're seeing the growth right now. Big data, advertising, policy, business, and analytics, so internal business analytics. And this is really where that 11% is coming from. You look everywhere, you see IBM getting into the business, all the startups in Silicon Valley, Palantir. It is incredible the growth that we're starting to see on this. And it's not just these big startup companies, it's also actually any company that wants to get more understanding of user data. So one of the big changes that's happening is that, let's say a Merck or a regular Fortune 500 company, they're starting to use this big data parallel computing HPC mindset. Bitcoin mining is another one. We don't have to talk about that. We don't need to care about Bitcoin right now. But also deep learning. So I think AI assistants, digital assistants. Actually, Jerry talking about the FIKE system that they were just talking about. That's an example of deep learning that very possibly was trained using this HPC mindset. So those digital assistants, Siri, whatever we have in the future. I joke, but it is progressing at such a rate that we are headed for real artificial intelligence more than we've ever seen before. So we have these open APIs that are freely available, and it's scaling right now as we speak. So
ComNet is coming?
That's what I'm saying, yeah. So yeah, Skynet may suddenly be, we might have Terminators on our hands soon. But Elon Musk would say that, so we don't have to talk about that. But one of the big growth sectors is these digital assistants, Alexa, Siri, Cortana, all that stuff on your phone. That's all based on deep learning, language processing, knowing what it is that you want out of the questions that you're asking. So that really is a growth sector. And then image recognition is something that you probably use every once in a while. If you ever put an image on Facebook, they use this machine learning algorithm to be able to take your face and recognize you so that they can tag you in that photo. And the way they do that is very interesting. They actually just run through millions of YouTube videos, and then the machine actually starts to realize that this image comes up a lot, and without anybody telling it what it is, it makes this map that ends up being a human face. So nobody programmed this image here. It just kind of, the computer figured out that this was important, and then somebody just put a label, human or man. So I always say that programmers are lazy. They don't want to program something they don't have to. So if the computer can learn it itself, then they're going to go with that. So, already we're seeing very quick growth in this sector. And then since it's YouTube, of course, we got an image of a cat. So a very quick side note, there's growth in other areas too, like, strangely enough, art. So if you feed a bunch of pictures into this deep learning, it can actually start seeing patterns that aren't actually there. So they fed this image into something called Deep Dream, and it came up with this kind of pagoda imagery because it was looking for pagodas there, and they just kept feeding it back iteratively. And this actually ended up in a art gallery in the Louvre. So it's amazing how we're branching into art with artificial intelligence. All right, so I don't know if I've convinced anybody, but if you were convinced, how would you buy into this? Well, the easy way, and the way that I think most people buy in, is to spin up an AWS, Amazon Web Services, public cloud instance. And the great thing about AWS is that they have this cloud-based GPU support. So you can actually spin up, without really much effort or time or cost to begin with, artificial intelligence or machine learning or anything like that on Amazon. Problem is that very, very quickly, that gets prohibitively expensive because they charge you by the compute core hour. And since we're talking about 2,000 cores for these operations just for one card, then you're paying out the nose very, very quickly. There are other smaller companies like SableCore, which is out of Florida, that provide, they're a 10-man unit that provides HPC on the cloud applications. And it's a similar buy-in to Amazon, but they're able to do it because of those GPUs that we were talking about and how much the prices come down. So that's the easy way, is to go to the public cloud. The medium is to use just standard, off-the-shelf x86 components to do this kind of stuff. And there are a lot of companies that are doing that as well. And it's something they can just put it in their own normal data center, and it still works. So it's kind of this quasi-HPC, just by loading the correct operating system on. And the hard way is to actually create one of these high-performance computers. And for a company like Merck that isn't a computer company, to get all of the infrastructure that's needed for that is very, very expensive. because they not only need the power for it, they need the cooling for it, and they also need the network for it. And a lot of companies don't necessarily have all of that in their existing data centers. So they might have to build a new data center to get everything that they need. All right, so now you're in, hopefully, well, maybe not, but now what? How do you actually start to implement this? And this is where we want to talk about colocation, because a lot of the infrastructure that is needed for this HPC computing is actually available in colocation, but not the standard everyday run-of-the-mill colocation where you have a raised floor, you have normal architecture for your electrical. This needs some kind of specialized system because it's just so dense, so powerful, that it just would not mix well with the existing systems. All right, so said before, lightning in a rack. So I want to just briefly touch on why we're saying that. One of these HPC clusters is 30 to 100 kilowatts per rack, which is a it's kind of an insane amount of power that we're using for this. Now, I'm comparing that to a bolt of lightning. So a bolt of lightning, the canonical definition is 1.21 gigawatts, which is a little low, but you multiply that by the amount of time that it takes to strike that bolt of lightning, which is 0.0022 seconds. So you get around 270 kilowatt hours out of one bolt of lightning. So you think 3 racks at 90 kW for 1 hour is equal to a bolt of lightning. So you're caging this incredible, one of the most incredible forces of nature in a rack. So how do you cool it? How do you power it? And how do you connect them together? And then how do you connect it to the rest of the world? So this is where colocation comes in. So space needs to be highly secure. It needs to have short cable runs so that everything can be close together, because these InfiniBand connections, they run at between 56 and 100 gigabytes per second. So they need to be close together because they need very low latency to make sure that all those computers can talk to one another. And then that makes cable management very key. So these have to be custom spaces, like we were saying. And you need very good air containment, because that heat could very easily go from the hot aisle, where it's coming out of the servers, back into the cold aisle. So it needs to have some sort of custom containment. And you need a low chance of air filtration from the outside, because it's very expensive equipment. You don't want to get messed up. And we think in general, but this isn't clear to everything, that a raised floor is not required, because especially if you're using the raised floor as an air plenum, it actually can't provide enough air as you need for these 30 kW racks. It's just the airflow, you would have to have so much air coming through that floor that it would almost just be prohibitive to do that. And so we think, in general, that this HPC should be segregated from the rest of the colocation. That it doesn't make sense to put this HPC units in with the traditional colo. So Agile Data Sites, for example, has designed high-performance computing vaults that are small rooms made specifically for high-performance computing. And they are designed for up to 30 kW per rack of air-cooled power. So the way we do that, one way is to have very tall racks, so 56U racks, so that we can fit as much as possible into this small space to keep that distance between all of the computers close. We provide custom power and cooling solutions for low PUE, so that they're very, very efficient. And in this particular case, these have very, very high security. So each one of those vaults that we're talking about actually has 8-inch cinder block walls. So you can't get much more secure than that to be able to, keep everybody out and have a secure entrance that only people who are part of the company that uses this are able to get into that room. So you think of traditional colocation, there are cages. That's great. Cages are great, but sometimes you can go under the floor. Sometimes there's a way to get around that cage. Whereas in this situation, There's absolutely no way that anybody else is getting into this room. And at the current time in this building, those aren't completed. We're still working on the construction of that, and you know, it's not something we can tour today. But we do have in this building 65 rooms that are capable of this kind of an architecture. Okay, so going on from space, power. So first thing about power is we need very flexible power, because like we said, every single one of these HPC installations is unique. So one way we do that is by using the Starline bus, which is an overhead busway, which, you know, could really be any kind of busway, but that way you can just take any type of receptacle, plug it into the bus, and suddenly you have the exact right power configuration that you need. It gives you very, very quick turnaround, and you can use any plug configuration or breaker size. We also have DC, so direct current options available. It's not something we've really seen too much in the marketplace, but we do have that capability, especially with HPC stuff. Some people want to have the most efficient electrical setup, and DC really is the way to achieve that. So it's available. We'll see if anybody wants it. And we do this, like I said, because no two HPC setups are the same. We're going to get very quickly into availability. Azure data sites at the moment can provide tier 3 level or above electrical distribution. So that includes 2 redundant generators, N plus N. So if any one of those generators were to fail, the other ones would take it up without any interruption. N plus N UPS, which is the same thing. If any one of the UPS units were to go down, no disruption. N plus N distribution, the entire side of the electrical distribution could be shut down, and we would still have all of the cooling power that we need. So, but to do that, we have N plus 1 crack units. And for 50% of those crack units, we actually dual feed them so that if the A side of the power distribution goes down, then the B side feeds those quote-unquote A side units. So that no matter what happens, we always have 90% of the cooling that we need. So that we've done computational fluid dynamics models, and we know that that will keep us within that ASHRAE TC 9.9 allowable range. And then lastly, you know, our power is very highly available from the street because we have 2 substations that come in opposite directions. One's about a mile west, the other one's about 2 miles east. So at the moment, we have about 5 megawatts here on site. In Allentown, we actually have an ungodly amount of power available, but we also here have a 69 kV circuit that's available on the street for future. So this is just going into what the architecture looks like and how we get that availability. And you can't really see it very well, but you can see there's a red side and a blue side, and in the middle is this green. So the red side is the A side, the blue side is the B side, and then this section in here is fed from both the A and B. So if the A side goes down, we still have 100% of the electrical systems and 90% of the HVAC systems. B side goes down, same thing. So that is a very high level of reliability. However, one of the great things about HPC is that they don't need that. A lot of times for especially specific applications, there are 3 different parts to the HPC architecture. There's a file system where you keep all your files and you connect to the network, all that stuff. Then there's these compute nodes, which are the things that actually do all those very complex computations. And then there's the network that puts everything together. So if you think about each of those, the file system itself, that can never ever go down because that's what's customer facing. That's the part that we really care about. That's when each one of these computations goes through, that's where the file that comes out of that is stored. So we never want the file system to go down. The network, we don't want to go down either because we have to restart that. We have to make all those connections again. And then we might lose our upstream, so we lose our customers. So we never want that to go down. But those compute cores that we were talking about, the things that actually do the work, they can go down. They're not that important. Those, we like to have the file system and the network on a tier 3 availability, but the compute could actually be a tier 1. Because after, these are iterative process, so one round through that computation, it gets saved to the file server, and then it'll send out another round through the computation, and then another round. So each one of those rounds isn't that important. It can just start where it left off. So those compute nodes can go down, and we don't really worry about it. So you can imagine, file system, we have all of this infrastructure upstream of the servers. So that's an incredibly complex, redundant. We have 2 generators, 2 switch gears, 2 UPS. That's very expensive. You're doubling up on everything. And it is incredibly reliable, but for the compute side, we really only need half of that. We need 1 generator, 1 switchgear, 1 UPS, because those can go down. So we're actually using half of the infrastructure for that compute side. And actually, in general, on this HPC stuff, the compute is maybe there's 10 times more compute servers and probably 20 times more electricity being used by those compute servers than for the file system. So we can save almost, many multiples of the cost to build out by having this hybrid tier concept. Okay, so that was power. Moving on from power is cooling. So there's really 3 different options for cooling that we'll talk about today. Air-cooled, so using normal airflow through a rack. Liquid-cooled, so that's actually pumping specific liquid cooling agent to the chip or to the heat source as closely coupled as possible. Or third, which is an emerging technology, is immersion cooling, where you actually take the server and dip it into a dielectric liquid. So we'll touch on that in a minute. But first, we'll talk about our HPC vaults, which use an air cooling system to cool up to 30 kW per rack. We do that by using rooftop air conditioners, which we do that because we can use outside air economization so that we can have very, very efficient systems. So we can use indirect air economization where we blow air past a heat exchanger and cool it down without using any refrigerant. Or adiabatic cooling where we drop down water over that heat exchanger to evaporate, which again greatly increases the efficiency. And to do that, we actually can see very low PUE and high energy efficiency. And the way that we know that's true is that we actually ran it through our own computational fluid dynamics model, which in a weird kind of circular logic is a high performance computing application that runs on the cloud. So we're actually using what we're talking about. But we designed it with these very, very large return and supply plenums so that the static pressure on the fans can be pretty low, but we still get that high efficiency of the air going through. So here's our CFD temperature plot of the HPC Vault that we're talking about. And you can see that the temperature in the cold aisle is around 60 degrees. It's pretty cold. But then the temperature delta into the hot aisle, because those servers are so hot, it gets almost up to 100 degrees. So this is a very specialized application where you're going from 60 degrees to about 100 degrees. And the great thing about that is that these rooftop air handler units really want to have high heat coming back. They run more efficiently in that kind of a configuration. So it makes it much more efficient to run this way than in a traditional colocation architecture. So I also want to talk briefly about our Allentown facility. We can do a certain level of that high-performance computing at our Allentown facility, but because we have a different architecture where we have in-row cooling units in that space, we can really only get to about 15 kW per rack. But that's still really in that HPC range. You can do a lot of applications with that type of a setup. We use high-performance chillers, and we can achieve a very low PUE, and those are actually available today, whereas the vaults have to be customized for a given application. So, talked about air-cooled. if we're talking about liquid-cooled servers, the way they do that is actually they have a lot of little pipes that go directly to the chip where there's water in and water out. That's great because water has a very high thermal conductance, which means that that water, you don't need that much water to cool a given chip, which can result in incredibly high efficient designs for these high performance computers. So we going back to this Tianhe Light HPC computer, which is again the fastest in the world. It's in China. It has that close coupled water cooling to the chip, which means that there's very complex piping within all these racks where there's one little pipe that goes to each compute core and then goes back out. It can be pretty difficult to maintain, and if there is a leak, it can be a major downtime event. So there are pluses in there and minuses, but it makes it the second most efficient computer in the world. So you talk about the flops, those floating point operations per second, per watt. That can be incredibly high with this type of a setup. You can get so much computation out of each watt that it blows traditional computing architectures out of the water. And actually, in this case, we don't have the exact numbers on how much this computer cost to build, but by every account, it was surprisingly economical to build this way. All the components to this were sourced in China, and compared to a lot of other systems that we've looked at, and we're not talking about engineering, but the actual components, this could actually be one of the most economical computers ever made as well. So moving on from liquid cooled, this is kind of one of my the things I'm most interested in personally, which is immersion cooling for servers. So you can imagine these are each vats that are filled with dielectric fluid. So these particular ones are filled with a non-conductive mineral oil. So you actually take the servers and immerse it in that mineral oil. So you take the server, dip it down in there, and then the mineral oil conducts the heat off the server chips directly. So the server chip is actually in that fluid and pumps it through a heat exchanger, which then can be cooled by a cooling tower in the yard outside. The great thing about this is that it's actually an electric insulator. So there's very low chance of shorts within this type of a framework. It actually helps preserve the computers themselves. And there's more than one way to do it. This is mineral oil. There's also ways to use a product called 3M Novec, where you would immerse this in basically it's a fire suppression liquid. And it can be even more efficient than the direct water cooling because the system itself is so simple. You're just dumping that cooler liquid in and taking it out, and the temperature delta between incoming and outgoing only has to be a couple of degrees because of the specific heat capacity of the liquid itself. You can fit so much more heat into the same volume. So it really is a good system, and we're looking for it. He's talked about the second most efficient supercomputer in the world was the Tianhe. The most efficient supercomputer actually uses this immersion cooling system. So you can have densities of 100 kW plus, but it's very expensive. It's almost prohibitively expensive for certain applications because you have to have so much of this dielectric fluid that you have to pump through the system. Now, it's coming down the price, but we'll see. It's just interesting to me. There's a little note on the side. If you were to imagine this entire building, I don't know, this building goes on for hundreds of yards in that direction, but if you were to imagine this entire building as one giant vat of this dielectric fluid and we filled it with servers, that would actually make somewhere around 193 square foot because we're not using the second floor. So 121,000 servers times 100 kW per rack is that 1.21 gigawatts that we were talking about earlier. So it would almost be, if we were to fill this entire place, it would almost be as if a bolt of lightning was coming down from the heavens at every second of every day, 24/7, 7 days a week, 365 days a year, and powering this place at that kind of density. Now, there's no way that's ever going to happen. Just saying it. It's just an interesting, it gives you an understanding of how much power comes out of these units. Okay, now we're moving to the network. You need two parts in general for these HPC applications. You need fast connection to the data that you're using and you're performing operations on, and you need a fast connection to the users themselves so that you can take that data and get it to who needs it. Okay, so first, fast connection to data. So HPC is data hungry. Whenever you're doing these applications, they need to have data to be able to get through the application, to do the machine learning or the analytics that they need. So for instance, Jerry was talking about the FIKE system. They had to take thousands of hours of video of not fire and fire situations so that that machine could learn what that looked like. And now I would venture a guess to say that that wasn't necessarily an HPC computer that did that machine learning, but there are many other types of systems that do use this HPC type of architecture. And for instance, that pagoda image that I talked about before, that was came from Google, and it's called Deep Dream. And so they needed a very, very fast connection to all those YouTube videos that they used to train it on what faces look like, or obviously cats look like. Wall Street, however, if you're doing some kind of machine learning on stocks or understanding Wall Street analytics, you need fast connection to the market data. So you'd probably put that near Wall Street or near whatever architecture or near whatever data you need there. And then we're going to talk a little bit more about analytics. So consumer analytics, customer data. You want just about every company needs to understand its customer. And that really comes down to the analysis that you can do on that customer. And right now, for example, Agile is in talks to obtain access to an incredibly robust network that supplies petabytes of data every day, of user data every day, so that if somebody, let's say, wanted to perform analytics and they had this HPC environment and they had everything but the data, we could supply that data at around 100 gigabytes per second at all times, daily, 365 days a year. So that is one of our differentiators for connecting the HPC to the data that they need. And then secondly, we need fast connections to the customer. So we have the data, we've analyzed it, now we got to get it to who needs it. So we need a high quality ISP backbone. So in terms of Agile data sites, we have a 5-carrier BGP setup so that if any one of those carriers goes down, the other ones pick up the slack. And we have the capability of 1 gig connections, and we can upgrade that as the user requires. And we also have partnerships with Synesis and Level 3 to provide high-quality fiber networks between our site and whatever customer site needs to connect. And we're working to acquire more dark fiber infrastructure. So this is the basic ISP layout. At this point, actually, Agile Data Sites is working on getting an ASN number so that we basically become our own ISP so that we can sell IP addresses to whoever needs them. But to do that, we blend our internet connection between these 6 carriers. There's actually 5. Verizon's not connected to the BGP. Don't have to talk about that, but Verizon is available on site. So we take all those, we connect them together at a dual router, and then we send that information over dual ports out to the clients who need them. They can have 500 megabits per second, 25 megabits per second. And then we have the same thing over here in Allentown. We actually, right now, have 3 suppliers, Level 3, Penteledata, and XO. And they come into the BGP on that side. And then we have a 1 gigabit point-to-point between the 2 sites. So this is a very robust network for our clients to be able to get their information out again. It works both ways, but in this example, we wanted to get it out. And we're also partnering with that same network that we were talking about earlier, has very high speed connection to Akamai. which is the biggest content distribution network out there. Now, what's a content distribution network? That's when you have your data, you send it to the CDN, the Content Distribution Network, and they have all these other computers, these nodes all across the world that take that data and aggregate it so that instead of sending it all just through a web of the internet, you send it to these node sites, and then they send it to a much smaller web. So instead of broadcasting to everybody from this site, we send to these smaller sites, and then they broadcast so that you're getting the data as close as possible to the user so that you're not using all that internet backbone, wasting your throughput on the internet. You're getting it to these node sites. So that increases the throughput, reduces ISP costs and bandwidth requirements. And you know, the network that we're developing has those direct connections where we can actually get 100 gigabits output from here to that Akamai network. And we think that's a big differentiator. So, okay, where are we now? HPC is here. HPC is important. It is where everything is going. And we believe that colocation is a good fit. And now, I know I've gone through a lot, but I don't know if anybody has any questions. So I am open if anybody does have any questions about what we went over. Okay. Yeah. Thank you very much.